Welcome to this quick yet essential dive into the world of material elasticity and its critical role in structural safety. From skyscrapers to bridges, every structure relies on the elasticity of its materials to ensure it can withstand the forces of everyday use and extreme events. In the next few minutes, we'll break down what elasticity means, how it affects structures, and why it's so important for safety. What is material elasticity? Let's start with the basics. Material elasticity refers to a material's ability to return to its original shape after being stretched or compressed. Think of a rubber band. When you stretch it and then let go, it snaps back to its original form. That's elasticity in action. However, not all materials behave exactly like rubber. Steel, concrete, and even wood have their own limits of elasticity, and understanding those limits is vital for engineers when designing safe structures. Elastic limit and structural safety. Now, every material has an elastic limit, the point beyond which it cannot return to its original shape. This is where things get critical. When a structure experiences forces, such as wind, weight, or even an earthquake, the materials within it stretch and compress. If those forces exceed the material's elastic limit, permanent damage can occur, compromising structural safety. Engineers must calculate the forces a building will face to ensure materials will only experience stress within their elastic limits. Young's modulus, the measure of elasticity. So, how do we quantify elasticity? Engineers use a value called Young's modulus. This measures a material's stiffness, or how much it will stretch under a given force. A high Young's modulus means the material is stiff, like steel, and resists deformation. A low modulus, like rubber, means the material is more flexible. By calculating Young's modulus, engineers ensure that the materials chosen for a structure can handle expected forces without losing their shape, ensuring safety under stress. Why elasticity matters for everyday structures. Elasticity plays a vital role in everyday structures. Take a suspension bridge, for example. The cables must stretch slightly to accommodate the weight of traffic, but they also need to snap back to maintain the bridge's integrity. Even in buildings, materials like steel beams and concrete must flex to handle loads and forces without permanent deformation. Properly accounting for elasticity ensures that structures remain both functional and safe. In conclusion, elasticity is more than just a material property, it's a cornerstone of structural safety. From defining the elastic limit to calculating Young's modulus, engineers rely on the elasticity of materials to design structures that are both resilient and reliable. Next time you cross a bridge or enter a skyscraper, remember that material elasticity is silently at work, keeping you safe. Welcome back to Blueprint to Reality. Today, we're exploring a fundamental structure you've probably seen countless times without realizing how crucial it is to construction: the truss. Trusses are everywhere, on the roofs of homes, in massive bridges, and even in stadiums. But why are they so widely used? What makes this simple framework so powerful? Let's break it down. What is a truss? First, let's define what a truss actually is. A truss is a framework made up of triangular units connected at joints called nodes. The key to its strength lies in the triangle shape, arguably the most stable shape in engineering. Unlike a rectangle, which can easily be deformed, a triangle maintains its shape under pressure, distributing loads efficiently across its structure. This ability to distribute forces evenly is why trusses are incredibly effective at carrying heavy loads. Trusses and roofs. When it comes to roofing, trusses are a popular choice for both residential and commercial buildings.
Why?
It's all about efficiency. Roof trusses allow builders to span large distances without the need for internal supports like columns or beams. This means you get more open space inside a building. The triangular configuration helps distribute the weight of the roof evenly across the walls, reducing the chance of structural failure. In short, trusses help create stronger, lighter, and more cost-effective roofs. Trusses in bridges. Now, let's talk about bridges. Trusses are commonly used in bridge designs, especially truss bridges, which can span vast distances while holding heavy loads like vehicles and trains. The secret? Trusses efficiently distribute the weight of the bridge deck across multiple points, making the bridge capable of handling enormous forces. A great example is the Forth Bridge in Scotland, one of the most famous truss bridges in the world. It's been standing strong for over 130 years, thanks to its truss design, which handles the dynamic loads of trains and natural forces like wind, efficiency, and material use. Another reason trusses are so widely used is their material efficiency. Because of the triangular design, trusses can carry large loads while using relatively little material compared to other structural systems. This makes trusses more cost-effective without sacrificing strength. Builders can use lighter materials, reduce overall costs, and still achieve high levels of safety and durability. In both roofs and bridges, trusses have proven their worth over centuries. They offer an ideal balance between strength, efficiency, and material savings, making them an indispensable part of engineering. Next time you look at a roof or across a bridge, take a moment to appreciate the power of trusses that makes it all possible. That's it for today's episode of Blueprint to Reality. Be sure to like, subscribe, and hit that notification bell for more fascinating insights into the world of civil engineering and design. See you next time. Welcome back to Blueprint to Reality, where we explore the fascinating world of civil engineering and architecture. Today, we're diving into a crucial but often overlooked aspect of building design: geometry. How do shapes and forms influence the strength and stability of structures? Introduction to structural geometry. Geometry is more than just aesthetics in engineering. It plays a vital role in determining a building's ability to bear loads and resist forces like wind, earthquakes, and gravity. The shape of a structure, whether it's a bridge, a skyscraper, or even a simple beam, directly affects its strength and stability. Triangles, the strongest shape. Let's start with the triangle. Known as the strongest and most stable geometric shape, triangles distribute force evenly along their sides. That's why you see triangular forms in trusses, bridges, and towers. The triangle's rigidity ensures that, when pressure is applied to any of its corners, the force is spread out across the entire structure, preventing deformation. Engineers use triangular frameworks in roof trusses and bridge designs, creating a network of triangles that efficiently manage both tension and compression forces. Arches and domes. Mastering compression. Next, we have the arch and dome, two geometric shapes that excel at handling compression. In an arch, forces are funneled downwards and outwards, allowing it to support heavy loads with minimal material. That's why ancient civilizations like the Romans used arches extensively in their bridges and aqueducts. Domes, which are essentially 3D arches, spread compression across their entire surface, making them incredibly strong and efficient at supporting large areas. Modern engineers still rely on these shapes for large spans, like stadiums and domed roofs. Hexagons and efficiency. Hexagons are another fascinating geometric shape used in engineering. Found in everything from honeycomb structures to carbon nanotubes, hexagons provide a balance of strength and material efficiency. Their ability to tessellate without leaving gaps makes them ideal for creating lightweight, strong structures. Geometry is at the heart of structural strength, influencing how buildings withstand the forces of nature. Whether it's the stability of triangles, the compression power of arches, or the efficiency of hexagons, understanding geometry allows engineers to design safer, stronger, and more efficient structures. Thanks for watching Blueprint to Reality. If you're fascinated by the science behind engineering, don't forget to subscribe for more in-depth insights.